Hi, welcome to part 2 of the video. In this part, we'll continue with the types of functions that we have, and then we'll study the number of functions of various types, and then we will move on to the composite functions. Now, in this part, it is important not to get confused from one topic to the other. So let's move into the lecture. Now, next we have many one function. In this part, what do we have? Unlike the previous functions, in the many one function defines that for a function f of a to b which is not 1 is many one function. Okay, that is, in the pool of all the functions, if it is not 1 then it becomes a many one function. That is, at least two different elements of a have the same image in b, or there exists an xy which belongs in a such that x is not equals to y, but my f of x is equals to y. It's very clear from the definition. Okay, let's look at the example. Let's say for some f or g from r to r, given by that there exists an xy which belongs in a, x is not equals to y, okay, are both many one functions, as 2 is not equals to minus 2, but f of 2 is equals to f of minus 2 equals to 4. Now can you give an example of this? This would be f of x equals to x square. Okay, now over here x can be equals to 2, which will give me 4, or x will be equal to minus 2, which will again give me 4. Okay, so that becomes an example of a many one function. Alright, now next to onto function. Now for an onto function, I define that my function from a to b is said to be onto or subjective if all the elements of b have pre-image in a. That is, for each element of b belonging in b, there exists some a belonging in a such that f of a is equals to b, or ab belongs in f. Now this symbol means there exists. Okay, don't get confused. Okay, so basically if there is an element b in capital B for some a in capital A such that my f of a is equals to b, or AB belongs in f, then in that case it becomes an onto function. That is, a function is not onto if there exists a b belonging in b such that there is no a belonging in a for which f of a equals to f of b. So basically these conditions needs to be satisfied for being an onto function. First of all, there has to be a b in b. These two are obviously prerequisite. Then it has to be in such a way that my f of a is equals to b, or my a b has to belong in f. Okay, now let's have a look at the example for this. For a function, I have ab for 1, 2 be the given function. Then I have these examples, the similar ones. Okay, now here 2 and 3 are onto functions as all the elements of B have a pre-image in A. How? In 1, 2 belongs in B but has no pre-image in A, and in 4 have no pre-image in A. 1 belongs in B, thus not onto function. For f a to b is onto function if the range of f is equals to the codomain of f is equals to b. Now this is the first important condition that you should look at. Next, how we prove that? Now for a range, we know that it is a subset of codomain, right, by definition. Now let this b belong in b, then if my function f is onto, it has pre-image in a, then b will belong in range f as range f contains those elements of B, right? Then my codomain f will belong there, thus my range f will be equal to the codomain. Okay? Now, to check subjectively if for a function, okay, take some element of B and then follow the steps given. Okay? Now, first let the function be y, express x in terms of y from the given expression like this. Alright? Now find the codomain of, first of all find the domain of g, the given function that you have gy. You need to find the domain of that. If the domain of g is equals to the codomain of the f, that is your b, then f is an onto. Okay, very three-step process and very simple. Alright, now if f this is satisfied, okay, then 0 of a will be greater than 0 of b. Okay, now let's move on to the into function. The into function says that for f a from a to b, which is not onto, is into function. Okay, the similar as 1 1 and many 1, that is at least one element of b have no pre-image in a, or there exists a b belonging in b such that there is no for which f of a equals to b. Okay, there is no element, alright, for which f of a is equals to b. Alright, now let's have a look. Let's say in an example, okay, for I have the previous examples, the functions 1 and 4 are into functions. How? Bijective functions or 1 1 or onto. Basically, if they are not onto functions, it becomes an into function. So a function is said to be bijective if it is injective as well as surjective. Okay, so it is an important point. If it is 1 1 and onto, then obviously it becomes a bijective function. Okay, now we can also say that for any function a to b, okay, is bijective if f is 1 1, okay, and f is onto, and the range of f is equals to the codomain of f. So in that case I'll get something like this, right? So the function is not bijective if it is either not injective nor a subjective. Okay, so in that case what will happen? I have 0 of a and 0 of b have this relation as well as this relation. So 0 of a will be equal to 0 of b. So in that case what will happen is I have my functions, it has to be subjective or bijective. Okay, so these are the differences or the similarities between 1 1, many 1, into and onto functions. Okay, for the next part I have the number of functions of various types. What are the different number of functions of various types? Let's have a look. Let there be a and b, two non-empty sets, okay, such that 0 of a is equals to m and 0 of b is equals to n, such that my f is from a to b be the functions from a to b. Now the number of functions from a to b, each element from a can be associated to n elements of b. Okay, basically from the left hand side, that is from a to b, different elements can be related to the elements in a. Okay, so basically what they are trying to say, for each element of a can be associated to n elements of b, so that the number of functions that can be formed from a to b is n into n times. Okay, so there will be n into n into n into n up till m times. Okay, so I'll get something like n to the power m. Therefore the total number of functions from a to b would be in terms of like this. Okay, 0 to b 0 of b to the power 0 of a. Alright. Now, the number of functions from a to b can also be every function is a relation but not vice versa. Okay. So, in this part, if you see, up till now you might have a certain functions which is, but this is where you might have felt that this is just like relation. Okay. So basically every function is a relation, okay, but not every relation is a function. Now if a and b are two non-empty sets such that 0 of a equals to m and 0 of b is equals to n, then number of relations possible from a to b becomes twice, okay, and the number of functions possible from b to n, a to b is n to the power m. Okay, so this is the difference. Okay, there is a huge difference from this to this. Okay, now the number of relations from a to b which are not functions is the difference of these two, or I can also write it like this. Okay, now the number of 1 functions. So each case will check how many numbers of functions basically exist. Now out of n to the power m function that we had, okay, from a to b some are 1 functions. Okay, now if we order the elements from 1 to m, say first, second, third, like this, if we order them, then for the first element of a we have n chances, and then it reduces to in the order of n minus 1. Similarly, if we reduce it from the set b, okay, so we will have the total number of 1 function possible would be this, that is, it becomes an npm relation. Okay, so we need to note over here that m has to be less than or equal to n, that is this. Okay, otherwise if m is greater than n, then in that case I will have this, no 1 function is possible from a to b like this way. Okay, now for elements in b there exist m minus n elements of a remains to be associated. Okay, therefore the number of 1 function from a to b will vary accordingly. Alright, just like this. Okay, now if you observe properly, you will find that out of n to the power m functions from a to b to the power, from a to b, okay, npm functions are 1. Okay, now this will be true for all cases. If m is less than or equals to n, then functions from a to b are many 1. Alright, just the opposite. We basically reduce it from the net and you will get the many 1 functions. And if I have my m is greater than n, then all the n to the power m functions are many 1 functions. Okay, now the number of bijective functions from a to b. For a bijective functions, okay, a function is bijective if and only if the function is 1 as well as on 2. Okay, so it is a combination, thus it implies that you need to satisfy both these conditions. Okay, so for that case, for the first element of a we have n options, and then for the second we have n minus 1 options, and so on it moves like that. Okay, so finally at last we will have only 1 option left. Therefore the total number of bijective functions from a to b is n factorial. Simple, n into n minus 1, and this way it comes to n factorial. Okay, now so for all bijective functions from a, I have this, b and this. Alright, so it will follow a path like this. Simple. These are the examples of these functions. Thus the number of bijective functions is n factorial if my m is equals to n, and if it is not, then it will be 0. Okay, now if you observe, from if 0 of a equals to 0 of b, then and the function is 1, then function is onto also, and hence it becomes a bijective. So what do we learn from this kind of function? If it is 1 1, then obviously it becomes a bijective function. Similarly, for such a case, if function is onto, then the function is 1 1 also, it becomes a bijective again, the vice versa of the previous one. Now we will come to the better topic of composite functions. Now composite function is the most important topic in this chapter. What is a composite function? It tells us that for any function from for a to b, I have, and for g, b to c, the two functions, then my g of f, okay, becomes a to c. Now what is g of f? Now I write like this, right, x square, okay. Now if I write g of fx, okay, it will be something like this. Alright, so this becomes my, this is what is called the g of f. Alright, so it can be defined as g of fx is equals to this for all x belonging in a. So this is called the composition of a of f and g. Basically any two functions, okay. So basically it is like if a to b, b to c, then it will be like this. Simple. Now how do we understand it more clearly? Now for g of f to exist, the range of f must be the subset of the domain of g, okay. Simple. Or either or the opposite if I have f of g, okay. Similarly for f of g, it has to be in the other way around. Now what are the properties stating a composite function? For a composite function, most important part is that the composite function is non-commutative. That is, f of g will not be equal to g of f, okay. Now it is also important that it is possible that f of g may not exist even if g of f exists. It's simple. There is no particular relation between g of f and f of g, okay. Now the composite function is associative. That is, basically if I have f, g, h, b, three functions, it is in this relation, then it will exist like this, provided that these three functions, they do exist. Alright. Now also if I have f and g are bijections, then g of f will also be bijection. Okay. Composite function of identity with any function is f itself. Alright, it's simple. Obviously if I have an identity function and if I compose it with the function, then it will automatically become the function itself. Now let's have a look at the questions based on the topics that we have just discussed. Now the question over here says, my first question is that the function f n to n, where n is this set of all natural numbers and defined as fn is equals to 2n plus 3, is a surjective, injective, bijective function or none of these. So you need to find what it is, okay. So what we will do is, in this question we will analyze this function one by one. We will take all the options into mind and start with it. So first thing that we check is, we will check for 1 1. So I let that fm is equals to fn, so it becomes 2m plus 3 is equals to 2n plus 3, which gives me m is equals to n. Therefore it becomes a 1 1 function. Now the other criteria that I need to check is, I have 2n belonging to n, right? Therefore f is injective only. But how to confirm it? I have fn equals to 2 also. So 2n plus 3 is equals to 2, okay. So n is equals to minus 1 by 2, which does not belong in n. Therefore, there is no pre-image of 2 belonging in n. Therefore, it is not an onto function. So, f is just injective only. Therefore, we need to note that 2n plus 3 is always an odd and in the range of 5, 7, 9, etc. and so on. Therefore, I have my answer as option number B. Now, the next question says that the function from R to R defined by fx is equals to x plus 1, x minus 1, x minus 2, x minus 3 is 1, 1 but not onto but not 1, 1, both 1, 1 and onto, neither 1, 1 nor onto. Okay. Similar to the previous question, over here also we'll do the step-by-step analysis. Okay. So let's start off with, first of all we'll check for 1, 1. I let the function become fx equals to fy, that is x minus 1 into x minus 2 into x minus 3 is equals to y minus 1, y minus 2, y minus 3. Okay. If I start solving this, I will get equations like this, a quadratic form obviously and then a linear form. Therefore, it becomes x cube minus 6x square plus 11x minus 6 equals to y cube minus 6y square plus 11y minus 6. This gives me x cube minus y cube minus 6 into x square minus y square plus 11x minus y equals to 0. Therefore, I have x minus y is equals to this. So, if I take this whole side on the right hand side, I will have x minus y is equal to 0 or this is equal to 0. So, from this I get that my x is equals to y, or then I have my x is equals to this complex thing. So, what do I do is, it is not 1, 1 for sure. Why? Because x equals to y not confirmed. Okay. So, I check for onto. Now, I here let b belong to the R, okay, in the codomain. So, f is equals to b. So, that is I check a minus 1, a minus 2, a minus 3 is equals to b. Now, this is a cubic in a, okay, hence there exists at least one root as complex root occur in pair. Okay. So, I get my f is clear to be an onto. Alright. F is onto but not 1, 1. Okay. So, alternate method, how do we do it? We draw the graph for the given function. Okay. So, I have my graph like this. Okay. For this function, it starts from here, cuts the x-axis as here, then again at over here, then again over here. Okay. So, clearly f is not 1, 1 as line parallel to the x-axis cuts the curve in more than one point. You see this line, it cuts at 1, 2, 3 points. Okay. Therefore, I have that clearly this is an onto function. Okay, and not 1, 1. Now, in the next question, I have my f is from 0, 1 to, which gives this, defined as fn is equals to n plus 1 when n is even, n minus 1 when n is odd. Check the function for 1, 1 or onto. Similar to that, we start with checking with 1, 1. I let fx equals to fy for some xy belonging in 0, 1, 2, 3, so on. So, in case 1, I take x and y both even. So, x plus 1 equals to y plus 1, x equals to y. Case 2, x even and y odd, x plus 1, y equals to minus 1. So, in that case, y becomes x plus 2. Therefore, if x is even, y cannot be odd. So, case 3 I take x is odd, y is even. In this case also I will have x equals to y plus 2. So, again y is odd, x cannot be even. So, these two cases doesn't help my case. Not possible. So, I have case 4. where x is odd and y is also odd. So in that case I can have my x equals to y. Okay, so what does this give me? X equals to y for f is 1 1. So I need to check for onto now. So for onto I have f of 0 equals to 0 plus 1 equals to 1, so 0 is even. But in odd cases I get 0 where 1 is odd. Again 2 is even, but here I got odd. 3 is even. So range equals to this, which is also my codomain. So f is onto also. Therefore f, the given function f, is 1 1 as well as onto. Alright. Now let's look at the next question. It says f a cross b is equals to b cross a. It is defined by f of a plus ab equals to ba is bijection for all a equals to this and this. How do I show this? We start with checking with 1 1. As we have done in all the cases, I start by letting f a1 b1 equals to a2 b2. So from this I will get b1 a1 equals to b2 a2, b1 equals to b2 and a1 equals to a2. So this will lead me to a1 b1 equals to a2 b2. Therefore 1 1 is there. Now I need to check onto. I let b comma a belongs in b across a, where b belongs in b, a belongs in a. So f of a comma b is equals to b comma a. Therefore f is also my onto. Okay, so over here I get it becomes 1 1 as well as onto. Alright, therefore it is a bijective function. Now question number 6 says the number of surjection from a equals to this for all n greater than equal to 2 onto b a comma b is. I need to solve this question. How do I start with this one? Over here I'll first let 0 of a equals to n, 0 of b equals to 2. This will lead me for n greater than equal to 2. I have my 0 of a is always greater than equal to 0 of b. Therefore the number of surjection on two functions will be given by the summation of this r over b, and this will give me this equation which says 2c naught into 2n minus 2c1 into 1 to the power n plus 0. So I will get 2 to the power n minus 2. So this will give me, we'll go through an alternative method here. Total number of functions from a to b is 2 to the power n. Number of function which is not onto, that is all the elements of a are either associated to a or b is 2. Therefore the number will be like this. You see, I can draw it like this, simple. The alternative method doesn't need much calculation, I just needed to map it. So I can have like this or like this. Therefore my onto function is 2 to the power n minus 2 in number. Alright. Hi everyone. Now while going through the lecture, if you have any queries, you can post it on our website. First of all, you'll have to go to askIITians.com, and in this over here you'll find ask a question category. When you go to this page, you will have ask experts. In this you select your category of question and post it over here. You can also post an attachment if you have any, or else press get answer, put in your email ID and other details and post it. So that was all in our part 2 part. Now in this part, what did we do? We studied the types of functions and then we moved on to the number of functions of various types. Also, we completed the part where we called it as a composite function. So that was all in our part 2 study. In the next part, in part 3, we will look at even and odd functions, and then we will move on to periodic as well as inverse of a function. So stay tuned for part 3.